Welcome to Lesson 81. Starting from this lesson, we will be learning how to solve ordinary differential equations. This type of equations, basically you're given a derivative function and you're going to look for the general function. When you take this general function's derivative, it will result in what's given to you as an equation. Before that, let's take a look at investigation 5. If you prefer to do this on your own, pause the video now. Investigation 5. When astronauts from the Apollo 15 spacecraft landed on the moon, one of the experiments they conducted was to test Galileo's theory that if two objects of different masses are in free fall in a vacuum, they will land at the same time, regardless of their weight. The moon was an ideal place to test this theory since its gravitational pull is minimal and there is no air resistance. So, one of the astronauts let a hammer and a feather fall from his hands at about 1.22 meters from the ground, and indeed, they landed at the same time. The acceleration due to gravity on the moon is about 1.625 meters per second squared. This is far less than that on Earth, which is about 9.8 meters per second squared. Number 1. Write an equation relating an object's acceleration due to gravity on the moon with the rate of change of the object's velocity, v. Hence, find a formula for v using the initial condition that t equals 0 and v is equal to 0. All right, so let's start by looking at number 1. What I also know from the given information is that the feather starts falling from a height of 1.22 meters. That means I can claim that the position at 0 is 1.22. And the acceleration due to gravity on the moon, let's call this a of t, is negative 1.625 meters per second squared. Okay, and that's constant. Using this information and also the fact that acceleration is the rate of change of velocity, so dv by dt is equals to a, I have negative 1.625 equals dv by dt. In order to find an expression for v, I need to get rid of the so-called derivative, so that means I must be integrating. And I have v on the right side here, okay? When I do this, I will have v equals to negative 1.625 t plus the constant c. Now we can sub in when v of 0, we get 0. So we have 0 equals negative 1.625 times 0 plus c, meaning c is 0, and therefore v of t, the velocity function, is negative 1.625 t. Okay. Number 2. Write an equation relating the object's velocity, which you found in question 1, with its rate of change of height above the ground s. Use the initial height of the feather and hammer to find a formula for their height above the ground at any time. So similar to what we did in part 1, we can say that velocity is the derivative of the position function s. So here I have negative 1.625 t equals ds by dt. In order to find s, I know I need to take the integral of this function with respect to time, of course. And this gives me s of t equals to negative 1.625 divided by 2 times t squared, which gives me negative 0.8 125. T squared plus C. I'm going to use the fact that S of 0 is equal to 1.22. If I plug in 0 into this function, of course, C is 1.22. As the result, S of t is equal to negative 0.8125 t squared plus 1.22. Okay. Okay, lastly, number 3, how long did it take the two objects to reach the ground after the astronaut let them drop? So number 3 calls for the time when the height of position is 0. Okay, so we're going to solve this equation. Negative 0.8125 t squared plus 1.22 equals to 0. And if I solve this by dividing 1.22 by that decimal number in front of t squared, square root, t is approximately 1.23. This is the only valid number that I'll get when I solve this equation. There you go. So you may be wondering, what does that investigation have to do with solving ordinary differential equations? That's nothing different, from what we have done before. Well, actually, when we say that we are solving a differential equation, it really means that you're working from an equation that involves derivatives to one that doesn't have it. So that's exactly what you did in number 1 and 2 in that investigation. The term ordinary means that there is only derivatives of one variable involved in the questions that we do. Some of you may actually take more math in university, and you'll be taking courses called differential equations. And in those more advanced like calculus or differential equation courses, you will learn more strategies to deal with what's called partial differential equations. And in those particular types of equations, you have at least one partial derivative involved. Like you'll have multivariable calculus, but that's not something you have to worry about right now, okay? Anyway, so let's use this particular example here to look at, what it really means to solve ordinary equations, or what it takes to find different types of solutions, so to speak, okay? So here, we are going to solve dy by dx equals to 4x squared. So here, we're trying to get rid of the derivative, so to speak, okay? So that means I can consider taking the integral of both sides of this equation. So what does that mean? I will have the integral of dy equals to the integral of 4x squared dx. Because the integral of 1 dy is y, and the integral of 4x squared is 4x cubed over 3 plus c. So we still have to include that integration constant. And notice that, we're really dealing with a family of functions here. There's a bunch of functions that looks like y equals to 4x cubed over 3 plus a number, or maybe plus 0 or minus a number. So that's when you take the derivative of this particular family of functions, you'll always end up with 4x squared. So we say that we have arrived at a general solution. Okay, so that's the notes on the side here. If you're provided with a particular point, like an initial value, then you can actually work out the value of c, like what we have done in the investigation. And when you are able to do that, then you will actually end up with what we call a particular solution. Okay, so now let's add on to this dy by dx equals to 4x squared question. And now we know that this function curve passes through 3 and 0. So what is the value of c then? Well, continuing from 0 is equal to 4 times 3 cubed now over 3 plus c, right? That was our general solution. we get c equals to, what is it? 3 cubed divided by 3 squared is 9, 36 negative. Okay, and now we have y equals to 4x cubed over 3 minus 36 as a particular solution to the differential equation. So here's another question. Is y equals to e to the power of x a solution to the differential equation y double prime plus 2y prime equals to 3y? Well, we can verify this by separating left side and right side of that differential equation and substitute the appropriate derivative of y, either the first or second derivative, right? And then perceive left side is equal to right side. Well, given that y is equal to e to the x, what is y prime? E to the x. What is y double prime? Also e to the x. Simple enough. Okay, so now starting from the left hand side, we have y double prime plus 2y prime. What is this? This is e to the x plus 2e to the x, which is 3e to the x. Now, right hand side is 3y. Subbing in y is 3e to the x, sorry. So since left hand side is equal to right hand side, therefore y equals to e to the x is a solution to the differential equation. Okay. You will also come across terminology like, oh, I have an order 1 or order 2 differential equation. What does that mean? Well, that basically describes the highest derivative that you have in your DE. So in the last example, I have y double prime plus y 2y prime. So the highest derivative we have is a second derivative. So that means we actually saw an order 2 differential equation. Okay. So differential equations come in different forms and shapes. And so in the next few lessons, we will be looking at specific types of differential equations and recognize their forms and look at strategies that will allow us to solve the different types of ODEs. Okay. So here we say that a differential equation in the form of dy by dx equals to f of x times g of y. So it's kind of like a product of a function in terms of x and another function in terms of y can be solved by the method of separation of variables. We can follow the steps outlined in this box when we solve this kind of DEs. You try to gather, okay? You gather all the y on one side of the equation, gather all the x's on the other side, and then you separate the dy by dx. And then notice that the dy by dx notation is not a division, okay? But again, we're not going to explain it too much here. And then you try to integrate both sides in order to arrive at a function of y in terms of x, okay? So let's put this into practice. Here is example 1. Find the general solution of cosecant x dy by dx equals to 1 plus y squared, and then give your answer in the form of y as a function of x. So let me copy down this equation here first. We have CSC x dy by dx equals to 1 plus y squared. And then we said, okay, we are going to keep all the y's on one side, all the x's on the other side. So what does that look like? Well, dy stays. I have 1 plus y squared on the right. I don't want it. Let's divide both sides by 1 plus y squared equals. Now I said that x's should go to the other side. So dx will go to the other side. Now I have cosecant, which is 1 over sine on the left, right? So when I cross multiply it to the other side, it becomes sine x. There. And then it looks clean enough now that in order to get rid of the dy dx, I have to integrate. So let's integrate both sides of this equation. The right side should be easier to deal with. I know that the integral of sine is negative cosine x. Let's put plus c on this side, okay? Well, how about the left-hand side? Do you recognize this pattern? You have 1 over 1 plus y squared. Maybe your formula booklet will be useful. So you may recognize that this is actually the integral of the function, arc tangent, but of y, of course, okay? So y is equal to the tangent of the right side, right? To get rid of arctan, you take tangent. So c minus cos x. All right. Here is example 2. Solve the dE for y given an initial value. So here you're given dy by dx equals to 4xy squared. And the initial value is y equals to 1 when x is equal to 0. So in this case, we're going to find a particular solution. All right. So let's follow the same steps. All the y's on one side, all the x's on the other side by either dividing or multiplying. Okay, so dy stays over y squared. 4x stays on the right, dx here. And then we have to integrate. Okay. So on the left side, I have y to the power of -2. I'm integrating that. So that means I'm going to add 1 to the exponent. -2 plus 1 is -1. Divide by -1, it gives me -1 over y equals. The right side, well, x becomes x squared over 2. So 4 over 2 is 2. So 2x squared plus c. And so if I take the negative reciprocal of both sides, I will get y equals to 1 over -c -2x squared. But I can cheat a little bit. I can really call this d to avoid having, a negative and negative again. Okay, so what's next? Well, we are looking for a particular solution. That means we must use the initial condition now. I'm just going to switch over here. Plugging in y equals to 1 and x equals to 0, I have d equals to 1. As a result, the particular solution that I'm looking for is y equals to 1 over 1 minus 2x squared. That's it. There are many useful applications of differential equations. We have seen it used a lot in estimating population growth, growth rate, flow rate of fluids, anything that has to do with change, really. Okay. So in our very first application question, we're going to look at salmon population. So example 3. Salmon population growth rate dP by dt is proportional to its current size p. A salmon farm has an initial population of 80. There are 120 salmon after 2 years. A. Write a differential equation model to model this population. So one of the key words that you notice in this question is proportional. There's no mention of a certain function, but this gives away the relationship between the rate of change, or the growth rate, dP by dt, and the current size. When we say that two quantities are proportional to another, it really means that as one goes up, the other one follows a rate of increase or decrease steadily. Okay, this means it implies a linear relation. And sometimes we call this constant k the proportionality, the constant. Okay, so those of you who took physics, you may remember, well, one of the things that when you do your physics experiment is really you're trying to establish, a relationship between the two quantities that you're studying, right? And you use this like fish symbol. This really the proportionality symbol. dP by dt is proportional to P, right? In this particular case here. Part B. We are going to look for the proportionality constant. What does that mean? Well, that means that I need to find K. And then based on the equation that we have established in part A, I can separate the variables and put all the P's on one side and T is on the other side. T is our time variable. K is just a constant, so we'll keep it on the right side, okay? And then by integrating both sides, I know I will be able to find a solution to this differential equation, and thus the number K. Because I'm also given that when time is 0, the initial population is 80, and when time is 2 years, 2, the population is 120. Okay, so let's solve this equation first. On the left side, I have the integral of 1 over p, which means that it's going to give me ln p. The right side is kt plus c. Okay, if I want to isolate for p, I know that it means I take e to the power of kt plus c. Notice how e to the power of kt plus c is actually the exponent law of the multiplication of the power e to the power of kt multiplied by e to the power of c. Well, both c and e are constants, they're numbers. So a simpler way to write out this solution is a times e to the power of kt, where we let a to equal e to the power of c. Okay, it looks a lot friendlier, and this is more, a common way to write this out. Okay, so we have to find out what a is, what k is. Let's sub in. At time t, population was 80. So I have 80 equals to a times e to the power of 0, really. So a is 80. This tells me that population function is now 80 e to the power of kt. But we still need to look for the value of k. So let's go to the side here. And we can now sub in the second data point, which is 2 and 120. I have 120 equals 80 e to the power of 2k. Okay? 120 over 80 is 3 over 2. To find k, I'm going to ln both sides of this equation. And I will have 2k times ln e, which is 1. Therefore, k is half ln 3 over 2. And if you like, you can also say this is ln of the square root of 3 over 2. So now we have found the proportionality constant. We have answered the question. But not only have we found it, we can also write out the particular solution. P is equal to 80 e to the power of 1/2 ln 3 over 2 t. Okay. This is useful for part C because in part C, we are looking for the population after 10 years. So after 10 years, we are at P of 10. So 80 e to the power of 1/2 ln 3/2 times 10. This means I have 80 e to the power of ln, while 10/2 is 5. This is 3/2 to the power of 5. Using our log property, e to the power of ln something is that something, right? So here we are really multiplying 80 by 3/2 to the power of 5. And then using your calculator, this works out to 607.5-ish. And the population after 10 years, we can't have half a salmon, so we can say 607 then. There are 607 salmons in 10 years. Okay. So a few notes at the bottom here, just to remember that when we talk about rate of change, we're really referring to a derivative, right? Because dy by dx. You can also think of the d's, like why are they d's? Get the deltas. Delta y over delta x, Greek letter d. Okay. And then when we say that something's proportional to x, meaning that it's a constant multiple of x. Therefore, we can write it as k times x. K is pretty generally used as a proportionality constant. So if something is inversely proportional to x, then it would be k over x, right? Because you're going the inverse way. And then the rate of decrease, it will imply that, well, your rate is decreasing. So you can assume that you get a negative derivative, okay?